My talk will be mostly based on a paper which we are finishing currently, together with some fantastic collaborators, Simon Carnot, Leonardo Rastelli, and David Simons-Duffin. I should also say that if there are any questions throughout the talk, please feel free to interrupt me and ask me. But I think we'll also have a chance to chat at the end. All right, so the talk will be about gravity, mostly. And in particular, some attempts towards a classification of theories of quantum gravity. So why is this interesting or important? There is an obvious experimental fact, which is that our universe contains gravity, so we should try to understand it. And in particular, we can ask the very ambitious question, what is the set of consistent universes? What is the set of consistent theories which contain gravity? Like we know very little about the answer to this question, extremely little. Like in particular, are there only very few options, or is there some vast landscape of possibilities? String theory certainly appears to be a consistent theory of quantum gravity, but we would like to know whether it's in some sense the only option, whether everything in one way or another comes from string theory. And then kind of an important feature is that well, how should I say? We don't necessarily have to try to classify all of the theory, including the R and the UV. Maybe it's enough as low energy observers. We care more about the long distance physics. So just try to understand what are the possible constraints, the general properties on the long distance physics. And finally, how does the answer depend on the space-time asymptotics? It could be that the end. It's probably the case that in ADS, flat space, and de Sitter in general, the answer looks very different. The first two cases are much easier to study, and that's actually what I'll focus on in this talk. But it would be interesting to understand this dependence on the asymptotics. Okay. So as I already said, one way to start attacking this question is to ask what are the possible constraints on the IR physics in the theories of quantum gravity. And there appears to be quite powerful constraints from consistency, which you would not see in quantum field theory alone. So there seem to be some perfectly healthy quantum field theories which become inconsistent when you couple them to gravity. This is sometimes called the swampland program. And there are many different swampland conjectures and sometimes even theorems which are part of the swampland program. One is that there should be no global symmetries in the IR. Another is the weak gravity conjecture, the distance conjecture, and so on. So you don't have to know what exactly these are to understand the rest of my talk. I just wanted to mention them. The reason I wanted to mention it is that while these conjectures are very powerful and beautiful, they have some drawbacks. One drawback is that they are conjectures. They are not necessarily rigorously proven, and many of the arguments are based on examples in string theory that these things are true in all examples in string theory, so we can extrapolate that they are true in general. There is a question in the chat. Okay, there's a question in the chat, why no global symmetries in DIR? What's wrong with the baryon number? Also, the idea would be that in a fully consistent theory of quantum gravity, there should be some high dimensional operators which break the baryon number. But okay, and what goes hand in hand with this fact that they are conjectural is that they are often just parametric bounds. That one can say that some quantity A is less than or equal to B with some undetermined constant, and we don't know really what the constant is, for example, in this distant conjecture. So what we would prefer is to have some more rigorous approach not just based on examples, but on general principles. And presumably, if we have that, this would allow us to prove not just parametric bounds, but precise bounds. Like we could say, that if this quantity is less than 3 times this other quantity, then it's allowed. If not, then such a theory cannot exist. So how do we do that? Well, there is one approach to this question is to use ADS-CFT, which says that so the general principle that quantum gravity in ADS is equivalent to a conformal field theory on the boundary. And in the case of conformal field theory, we know exactly what the axioms are. What are the general principles? This is known as the conformal bootstrap, and it leads to some very powerful exclusions with very precise bounds of the form A less than equal to some number times B. Okay. You can say if you are outside of this island, this is not allowed, and if you're inside, it's allowed. But we currently don't really have the analog in the quantum gravity regime. One would really like to find some islands maybe in the space of theories of quantum gravity. So even though the general principle should be true, in practice, this has been quite challenging to apply the, say, the numerical bootstrap to quantum gravity. But okay, the general idea should somehow work, that to use the conformal bootstrap to constrain quantum gravity. Now, let me tell you a bit how I started thinking about this question. So I started with a question which is not really related to quantum gravity per se. It's slightly more general. And it's that there's a basic issue with the conformal bootstrap, which is that mostly the bounds are numerical. You need to put it on a computer, do some numerics to find the bounds. But to really improve our understanding, we would like some analytic proofs of these bounds. For example, if you could prove analytically that the Ising model saturates a bound, then this would presumably solve the 3D Ising model analytically. But we are still far from that, but it's the hope. So this is the plot in 3 dimensions, where we still have no idea, well, we have little idea about the precise analytic mechanism. But there is a simpler problem, which is what I started thinking about in 2016, which is in CFT1. So in CFT1, this the bound with the kink becomes just a straight line, which is some free fermionic theory saturates, well, numerically saturated the bound. And I asked the question, how do we prove this analytically? And this was actually possible. So I came up with an analytic proof of the optimal bound. This was done in the CFT1 for the first time in 2016. And the idea goes under the name of analytic functionals. I don't really want to go into the technical details of it because they won't matter for the rest of the talk, but the basic idea is that you integrate a crossing equation against some kernels in a complex plane, and by contour manipulations, you can prove the theorem. And then the functional then looks like this. It's some wiggly thing which constrains the low energy spectrum. But this is just some pictorial representation of the technical details won't matter. So at first sight, this seems like a completely unrelated question, maybe to quantum gravity, but it actually turned out to be exactly the right question to ask to attack the problem of quantum gravity using the bootstrap. So first, we generalized my technique from 1 dimension to several other cases, like ADS2 CFT1 and boundary conformal field theory. Then in 2019, with Tom Hartmann and Leonardo Rastelli, we generalized this technique to the modular bootstrap and proved something about conformal field theories with large central charge, which are dual to gravity and ADS. And we also found some interesting connection to the sphere packing problem. Actually, these analytic functionals are exactly the same method that the mathematicians used to solve the sphere packing problem in 8 and 24 dimensions. We were quite surprised to find out. So in some alternate universe, you could imagine that physicists would have solved the sphere packing problem before the mathematicians in 8 and 24 dimensions using these analytic functionals. But unfortunately, we realized this after the sphere packing problem was solved. Finally, then in 2019, we generalized this to d-dimensional conformal field theory and found some interesting connection to dispersion relations, which will play an important role in the rest of this talk. And I'll review all of this in more detail. So somehow the idea is that the analytic functionals are actually completely equivalent to, well, they give a different way of looking at, fruitful way of looking at dispersion relations in conformal field theory. That was discussed in our paper from the last summer. And finally, in the work to appear soon, we will explain how how to use this idea, the analytic functionals and the dispersion relations, to constrain quantum gravity in ADS. So this is how we started thinking about the problem, but actually during the course of this collaboration, we realized that it's much simpler. Well, there is a parallel but technically simpler story in flat space, and that's what I'm going to talk about today. The rest of the talk will be in flat space, and provided there is some time at the end, I'll come back to the ADS CFT picture and the dispersion relations in the context of CFTs. All right, so this is just to explain to how this fits into my way of thinking about conformal field theories and the universe. But let's now get to business. Here's the roadmap for the rest of the talk. I basically need to do three things. I'll need to explain to you what is the space of a priori parameters that we are going to constrain. And the answer is that the parameters will be the higher derivatives, irrelevant couplings in the effective field theory of gravity. The second point will be to explain what are the fundamental principles, the assumptions that go into the proofs. And the answer is that these assumptions are nothing but the fundamental principles of causality and unitarity. So it's quite general. And finally, I'll have to explain how to use the point 2 to put bounds on the parameters. So how to use causality and unitarity to put bounds on the a priori parameters. And the answer to that will be, well, to use dispersion relations in some relatively novel way. So that's the outline for the talk. And unless there are questions now, I will start explaining about point 1.
So may I ask about assumptions, because we don't live in ADS and don't live in flat space, we live in de Sitter space. In particular, most likely we live in metastable vacuum also. To what extent these bounds are, like, is the assumption, for instance, that it's stable vacuum, what you constrain in?
So my instinct is that at the level where we are working, well, this shouldn't matter. In particular, the answer turns out to be the same in ADS and in flat space, but for somewhat technical reasons. But so I would imagine that because the answer is the same in ADS and flat space, it would also be the same in de Sitter. Do we assume a stable vacuum? I would say yes. So certainly, yeah, we do. Well, sorry. Maybe if the lifetime is very long, this won't matter. Well, perhaps ask me this question later. If you're not satisfied with the way I explain it. All right. Any further questions about this broad picture? Okay. If not, let me explain to you what these parameters are. So we'll work in the context of the low energy effective field theory of gravity. So if we forget about some other light or massless particles, at low energy we can describe gravity using some effective action, which looks as such. So there is a coupling which is G Newton, and the leading term is just the Einstein-Hilbert action. And that there are some higher derivative corrections. So schematically, the leading ones are like, they contain 2 powers of the Riemann tensor and 3 powers of Riemann tensor, but there's an infinite sequence of corrections. One striking feature of this action is that all of the interactions are irrelevant. The lowest dimension operator is the Einstein-Hilbert term, which is irrelevant. The Newton's constant has a negative mass dimension, and we can write it. It implies the existence of some scale known as the Planck scale. So I'll denote the Planck scale as MP, M Planck, and the Planck scale, which is units of energy, is related to the Newton constant as such. So when a Newton constant becomes small, the Planck scale becomes large because D is greater than 2.
So here lambda equal to 0 is an assumption, right? I mean, there is the cosmological constant.
Oh, that's right. Yeah, that's right. Okay, I should say that that for now I'm in flat space. Okay. Thanks. Essentially, for in the whole talk I'll be in flat space. Okay. Now the idea is that this action can be trusted as long as the energies are sufficiently small. There is some UV cutoff where some new particles may appear. This cutoff is expected to be below the Planck scale because at the very least gravity becomes strongly coupled to the Planck scale, and as long as the energies are much smaller than the UV cutoff, this effective field theory can be used. This goes hand in hand with the expectation that these higher derivative couplings are suppressed by powers of the cutoff. So, for example, this alpha 2, which has dimensions of length squared, will be suppressed by the UV cutoff m to the -2, and alpha 3, which has dimensions of length to the 4, will be suppressed by 4 powers of the UV cutoff. That's at least the folklore, the expectation of general principles of quantum field theory. And this expectation was attempted to put on a firmer footing in this beautiful paper by Kamanho, Edelstein, Maldacen, and Chibuedov, whose main points I'll review soon. But we have never, people haven't been able to prove actual bounds on these couplings. Okay, so one goal which motivates the bulk of this talk is to prove some rigorous bounds on these coefficients in front. Okay, so essentially what C, E, and Z showed that if these coefficients are larger than the UV cutoff, there's a problem. But they didn't really show how exactly how much larger they have to be. So what we want to put some actual numbers into these inequalities and say that in every consistent theory of gravity in the low energy, alpha 2 is bounded by some number times m to the -2, alpha 3 is bounded by some number times m to the -4.
Okay. What about the sign? You put an absolute value there, but what about the sign of the coefficient?
Right. So I think that's I don't think that. Well, first of all, I should say that I will not prove such bounds in this talk. I will work in a simpler model, and in that model, the signs are not definite. Yeah. So as I'll discuss, there are some examples where one can show bounds, some negativity or positivity bounds on operators. This is not really the case in this case for these alpha 2 and alpha 3. They may be negative and positive, and in string theory, they are either 0 or positive. There, so alpha 3 is positive in the heterotic string. So we don't really have examples where they are negative, but I don't think there is a proof that they cannot be negative. Finally, you can complain that, well, these are some irrelevant operators. So by definition, they're irrelevant. Why should I care about them? But actually, maybe if they could be measurable. If inflation happens, if the Hubble scale of inflation happens around the scale of the UV cutoff, then inflationary correlators will be sensitive to these corrections. So it makes sense to think about them and study them.
I think there is a question in the chat.
Oh, okay. Let me see. So there's a question in the chat. Oh, the question is, you're not including matter. Why is that? I just wanted to write down the simplest toy model, but well, not the simplest model where there's only gravity, just to make a simple point. But the technique that I'll describe is also able to include matter. Like you can include matter and it will still work. So the first step is to realize that this is actually an interesting question already in weakly coupled theories. So let me give more detail. So again, here is the action for gravity. And you may think, well, you can have an ambitious goal, which turns out to be overly ambitious, which is to say the following. Well, I know that there is a Planck scale, so perhaps I should be able to prove that all of these coefficients are bounded by powers of the Planck scale. That's the natural scale of gravity. But this actually cannot be true. The reason why it cannot be true is that there's a counterexample provided by weakly coupled string theory. So when you consider string theory with string coupling much smaller than 1, so this is the G string, the dimensionless coupling, the spectrum of the theory looks like this as a function of energy. At 0 energy, there are some massless states like the gravitons. Then there is a scale, which is the true UV cutoff, which is the string scale, where massive excitations of the string live, and the scale is given by the Planck scale times this G string to some power. So this is some small number. So the string scale is way below the Planck scale. And finally, then there's the Planck scale where all sorts of crazy things can happen, like black holes and so on. So in this theory, in a weakly coupled string theory, the UV cutoff is at way below the Planck scale, and correspondingly, these coefficients like alpha 2 and alpha 3 are not suppressed by the Planck scale, but by the string scale. Okay, so like showing this is unfeasible.
Actually, isn't it often said that in some sense the expectation is the opposite? There should be some like lower bound on these guys, because essentially because there is no such a thing as pure gravity, and there should be some lower cutoff.
Yeah, that's right. I mean, you would expect that if not just that there's an upper bound, but also when you actually have states at this scale, then the coefficients should appear with those bits at that scale. Yeah, totally. So okay, just to explain this point, the natural first goal is to prove bounds in the case of the weak coupling. So we imagine that in some sense the G string is much smaller than 1, which means that we are taking some limit where this G Newton becomes very small, and keeping the UV cutoff M fixed and alpha 2, alpha 3 fixed. So basically this means that one was working at tree level, at least from the point of view of the low energy effective field theory. And in this context of the weak coupling, one can try to prove that there is some relationship, maybe a lower bound, or as Sergey suggested, a lower bound on the alpha 2 of the form some number times m to the minus 2. In this, so this is the regime, and similar for alpha 3.
Dalimil, so when you say you want to prove a rigorous bound, that instead of a parametric one, that must mean, I mean, then you also need a rigorous definition of the cutoff, right? Not just a parametric definition of the cutoff.
Exactly. Yeah. That's an excellent point. It will be explained later, but I can sketch it now. It's just it will, in these weakly coupled theories, there is a very precise way to define the precise place of the UV cutoff, and that's just where the S-matrix develops imaginary part in the physical region. It's where the exchanges, the string exchanges would start. So literally the location of the first string exchange, so the start of the cut, the unitarity, start of the branch cut of the S-matrix.
Sorry about the gravitons.
Oh, sorry, I think someone's asking a question, but it's very quiet.
I think that was background noise. I muted the person.
Oh, okay.
But there is a question from Glynis in the chat. Why? Yeah.
G Newton is not. No. G Newton is identified with 1 over m Planck. So there's some small parameter G Newton which is tied to m Planck. M Planck is very large, and then the UV cutoff is way below the Planck scale. Another question? Yeah. Okay, so okay, it may seem like we are assuming weak coupling, so it's boring, but actually it's not boring at all. We know we know very little even about this weakly coupled question. So more generally, we can try to classify what are the weakly coupled theories of gravity. And in fact, there are only three known examples in flat space. There's the S-matrix of the Einstein gravity, the S-matrix of the heterotic string, and the S-matrix of the type 2 string. So the interesting point is that at tree level, the S-matrix doesn't depend on the details of the compactification. It's always the same. And this is some point which has been emphasized by Nima and was recently studied in this pair of papers. Okay, so as I said, one can ask, is this the complete list of allowed weakly coupled S-matrices in flat space containing gravity? And there is also a related question in the absence of gravity, which is to study theories of weakly coupled higher spin massive particles. So some infinitely many massive higher spin particles, and how can they interact consistently at tree level without violating causality and unitarity? And this may lead to, well, certainly large and gauge theories are examples of such as matrices, and one could try to hope to classify them or at least study them from this point of view. And some nice progress was made in this paper by Simon, Zohar, Amit, and Sasha in 2014.
Sorry, I don't know. Coming back to a question by Matt. I thought that in these weakly coupled situations, there is a kind of positivity bound, right? Coming essentially from absence of time advance. I thought that was the point of that paper by Juan and friends to show that.
Oh, no, it's, well, I think, no, I think in that the point of, you mean the CEMZ paper?
Right.
There, I don't think that they show positivity. They show parametric suppression of the higher derivative corrections. Yeah, I will discuss this a little bit more. Maybe it will become clear why it's a little different from the positivity bounds which you have in mind, which I guess are going to appear soon in this on some slides.
It sounds like your next slide is about that.
Yeah. Well, actually, yeah. Okay. So, right. So, what is the physical idea of these bounds? There are essentially two approaches so far. One coming from this beautiful paper from 2006, co-authored by Sergey, and the other one comes. The other idea comes from this paper that I already quoted by CEMC. And the idea is that when these, right now I will focus on the second paper, but the connection to the first paper will come later. So the idea of the CEMZ paper is that too large, when the irrelevant couplings are too large, you get superluminal propagation of signals. So here's the thought experiment that CEMZ considered. Now I'm just reviewing the argument. You imagine a pair of particles in a theory of gravity. So there's some high energy particle, that's the red one, going along the x minus direction, so propagating essentially at the speed of light. That goes very fast. And there's a second probe particle. And the idea is that this is like a classical argument. So classically, this first particle is going to create what is called a shock wave. So it sort of back reacts on the gravity, on the metric, and it creates some background in which this other particle propagates. And this because there is some non-trivial background, the probe particle is not going to follow a straight line, but actually makes it a discontinuous jump. There's some singularity in the metric which causes this jump. And the jump has the following form. So this is, well, first of all, I should say that to maintain causality, this jump should be positive. If delta x minus becomes negative, the particle effectively goes back in time, and you will get a violation of causality. Okay, so here is what the jump looks like. First of all, there's some overall prefactor, which is proportional to the energy of this mass of this fast particle. And an important point is that it depends on the impact parameter. So here, what I showed is just a two-dimensional slice, and there's also a set of transverse directions, which is in this transverse direction, the probe particle can have a non-zero impact parameter b. So b is the impact parameter, and the delta x minus depends on the impact parameter. And there is this bracket which shows the time advance, or time delay, which at the leading order, there is just one. That's the answer in Einstein gravity. But there are corrections coming from the higher derivative operators. And depending on the polarizations of this graviton, of the blue graviton, you can get plus or minus sign. Now, for consistency, we need this bracket to be non-negative. And you can see that if we take b very small, then the third term is going to dominate, and we can always, no matter whether alpha 3 is positive or negative, we can arrange for this to be negative. So that means that there's going to be some problem if alpha 3 is too big. And how big is too big? Well, to find a problem, we need to take a very small impact parameter. But in a theory where there's a UV cut of m, we should not be allowed to take the impact parameter smaller than that, because there you need to worry about producing the particles, the new heavy particles. Okay, so that means that there are these parametric bounds that alpha 2 and alpha 3 in absolute value should be parametrically less with some undetermined coefficient than the minimum value of the impact parameter that we can take, which is the inverse of the UV cutoff. Okay, so this is a beautiful argument, but it has the downside that it doesn't allow us to prove precise bounds. So we would like to replace these parametric bounds by precise inequalities and find these coefficients. So in principle, there should be a well-defined answer to the question: what is the allowed region in quantum gravity theories for this alpha 2 times m squared and alpha 3 times m to the 4? We still don't know what this allowed region is. So as I already mentioned, the type 2 string theory, weakly coupled type 2 string theory, lies exactly at the origin, and the heterotic string has a vanishing alpha 2 and non-vanishing alpha 3. There are no, and these are the only examples that we know are for sure UV consistent. Okay, so that's what we want. Basically, we want to prove, we want to find this plot. Okay, is this argument roughly clear? Are there any questions?
This argument seems to work also in the presence of matter, right?
That's right. Yeah, yeah.
Because
well, yeah, I think. Well, this yeah, I think the answer is yes. And well, actually, in fact, that's what I'm coming to now, which is the main result of the upcoming paper and of this talk is to consider a slightly simpler problem, namely a problem of gravity together with a massless scalar. So in the rest of the talk, I'll explain how to prove the analog of this plot, not for alpha 2 and alpha 3, but for some couplings in this theory of a gravity and a massless scalar. So this is the low energy action. Again, there is the G Newton in front, which is very small. And there is the Einstein term. And then we have a massless scalar field phi. So phi has a kinetic term. It's a massless real scalar. It has a kinetic term. There's no mass term. Then there's a usual phi to the 4 interaction and an infinite sequence of higher derivative interactions. And the two coefficients which we'll care about, which are very closely related to the alpha 2 and alpha 3 from the previous slides, are these two. So there's the story generalizes to higher derivative interactions, but I'll focus mostly on this beta 2 and beta 3, which multiply the 4 derivative and the 6 derivative term. Okay, and so this is the goal.
Excuse, can I ask you a question?
Mhm.
Isn't this theory already ruled out by the absence of Fiff's force?
By the absence of what? sorry?
The Fiff's force, you know, additional scalar force. This is a massless scalar, you said, right?
You mean in our universe?
Yeah, in our.
Yeah. Probably. Yeah, that's a good point.
Mhm.
I wasn't really aware of it. I don't follow some experimental results that closely, but I would love to. I guess it makes sense. This would be a massless scalar force would be a very obvious experimental error.
Well, it depends on how pi couples to matter. But actually, you set the mass equal to 0, right? The mass of the scalar equal to 0.
Mm-hmm. Yeah, it's a simplifying assumption. It's not important.
So you can also add relevant parameters to your theory when there are light fields, and you don't expect this to change your argument, do you?
That's right. Yeah, for a reason which I'll explain. The relevant couplings do not in some sense the relevant. The idea is that causality requires some communication between IR and the UV, some connection between IR and the UV, and these relevant parameters don't talk to the UV. They are some parameters of the IR theory that you can freely adjust, and that for that reason they are not constrained by this argument. And
but by the way, my question was when coupling is even 0. Of course, if coupling is there, the tree level is ruled out plain. But if coupling is even 0, then there is a gravity loop generated effective coupling. And that's what my question was about. I suspect that even that is ruled out.
Oh, okay.
But that was a question, not a statement.
Oh, okay. Okay.
Yeah. May I ask you also about the previous discussion with alpha 4, alpha 2? So in what number of dimensions that was example? Because I thought in 4 dimensions R squared operator vanishes on shell, right? There is no R squared operator in 4 dimensions.
That's right. Yeah, this is in well, strictly speaking, it works in 4 dimensions and more. In 4 dimensions, there is some special thing happening, which is that what's it called? The Euler density is topological, so alpha 2 doesn't exist. There is an additional complication that there are really 2 kinds of alpha 3, a parity odd and parity even. But yeah, it's a detail.
So this is discussion in general number of dimensions.
Yes. Yeah. Okay, so coming back to describing our main result, we assume that there's a UV cutoff exactly at M, which I'll explain. Following up on Ken's question, I'll explain more what it means to be exactly at M, and also that the theory is weakly coupled, namely the Planck scale is high above the UV cutoff. So in this theory, we found these bounds. So everything to the right is allowed, and the bounds are in different colors, correspond to different dimensions of space-time. Horizontal axis is the B2 is the 4th derivative coupling. Vertical is the 6th derivative coupling. So the claim is that any weakly coupled theory must have these quartic interactions lying to the right of the bounds. And there is some interesting kink that we don't know what exactly is the theory lying at this kink. We know the spectrum of the theory, which I'll show it later. It would be interesting if it was some new theory of gravity, but probably it has some other problems. But okay, another feature is that the parameters, the allowed space is not compact. There is the beta 2 can be made arbitrarily large in the n positive. So that's essentially because to every solution with gravity, we can add a solution without gravity, and without gravity, this 4th derivative coupling must be positive. So that generates the non-compact positive direction to the right of the plot. And to my knowledge, this is the first rigorous derivation of these bounds. Bounds depending on the UV cutoff in the presence of gravity, or more generally, it's just general bounds on couplings in the presence of gravity.
Can you explain what you mean by assume the V cutoff is exactly at M? I mean, how precisely? This is going back.
Yeah, I think it's coming in like 2 slides, if that's okay.
Sure.
Oh, actually, in 1 slide. So now coming to the point 2, what are the fundamental principles and assumptions of this? So to show those bounds, we'll just use the S-matrix, the 2-to-2 scattering of the massless scalar phi, and we'll write it in the usual way. As the scattering amplitude is a function of 2 Mandelstam variables, S and T. And it's important that we are using a Lorentzian observable. And from the Euclidean point of view, there is nothing too wrong with like an EFT with pretty much arbitrary couplings. And it's important that these problems arise from a Lorentzian point of view. This superluminality, etc. It's a Lorentzian effect. Okay, so here's the answer to the recent question. What does it mean that the cutoff is exactly at m squared? Well, consider this function, this amplitude, as a function of s and t, keeping u fixed. So as maybe I should have said this, that s plus t plus u is 0, the sum of the 3 Mandelstams. So we are keeping u fixed, and s varies, and together with that t varies because it's tied to the value of s. And then this function looks as follows. It has cuts on the real axis of s. This cut on the right is the s-channel cut, corresponding to the exchanges of on-shell s-channel particles. And what I mean by the cutoff being exactly at m is this, that the cut starts exactly at m squared.
Oh, sorry, but you have, in your theory, you also have massless gravitons and massless scalar. So there is a like full cut starts really at 0.
Yeah,
right?
but at weak coupling, these are subleading effects. So I'm working at the leading order in G Newton. So it's like a tree level computation. So there's an EFT here. Okay, there is some logarithmic effect, but they are negligible in the limit where I'm working.
But the question, because you're saying that can be used to rigorously define what cutoff is. If somebody just hands you this function, like this answer for the amplitude, how if you have the answer, how from the answer you extract what the cutoff is? Because there is a cut which goes all the way to 0, and you don't know. If you just know this function, but don't know its parametric dependence, so how you?
Well, say for example, in string theory, the answer is straightforward. In that case, the theory is weakly coupled. The tree level amplitude is weakly coupled at all energies. You can look where is the first massive pole, and that's where the cutoff is. So there are some massless pole. At the leading order in G Newton, the only singularities are massless poles over here, and some massive poles on the positions of the cuts. Okay, maybe I could have drawn this as a sequence of discrete poles, which would look more like the tree level answer. Does that help, Sergey? Like I of course agree. At finite coupling in the quantum theory, there is a massless cut stretching all the way down to 0. But this is not.
My confusion is because I got an impression before from how you answered to Ken that you have a like rigorous definition of this cutoff just from looking at the amplitude, not making any assumptions what the theory is.
Yeah, no, the whole discussion assumes weak coupling. So in that case, weak coupling of the EFT. Okay, in the extreme limit where m Planck is infinitely larger than capital M, this is a rigorous definition of where capital M is.
But there is also, isn't in your Lagrangian, didn't you also have self-interactions of scalar field? Which is not Planck suppressed, but there is also.
But well, here I'm making the assumption that they are Planck suppressed. There's sort of an overall. I'm putting the G Newton in front of everything, and all the couplings, just like in tree level string theory. Just like in tree level string theory, all of these couplings go to 0 at the same rate, and M Planck goes to infinity. And
well, but they're not suppressed by Planck, they're suppressed by scale.
Yeah.
Like it depends on beta zero, right? If beta zero is large, then scalar field self-interaction suppressed by different scale. Like that, I thought that was your capital M scale is, and that means
capital M is like the string scale.
right. So that's what sets self-interactions strength of field phi, and if field phi is massless, that means there is a cut which goes all the way from zero.
Well,
with the strength suppressed by M.
Just I mean, the example where all I'm saying is very clear is tree-level string theory. They're all of string. What does the amplitude look like in tree-level string theory? There is some overall G Newton multiplying tree-level answer. Okay, and I'm looking what multiplies the G Newton. It's some function of ST and U, which is meromorphic. And from this function of ST and U, I can extract this beta 0, beta 2, and beta 3, and they are all finite for finite alpha prime. Right, so I'm factoring out the G Newton, looking at the coefficient of G Newton in the answer, and they're expanding that.
So beta 0, I'm actually very confused. So beta 0 has dimensions of inverse mass, right? Inverse mass squared. The way you've
beta zero, yes, sorry, that's right there.
So what is it suppressed by? I'm completely confused. Is it
beta 0? Well, I guess whether beta 0 is suppressed or not depends on space-time dimension. It just depends on whether phi.
Okay, let's say in 4 dimensions.
In 4 dimensions, it's marginal.
Well, it would be marginal if you hadn't factored out the G Newton. I mean, the whole coefficient is.
Yeah, well, again, in 4 dimensions, it's a sort of free parameter which is not constrained by this discussion.
But are you assuming that it's weak so that you can make this argument about ignoring the cut that goes to 0 then? Or
yeah, that's right. Yeah, I'm assuming this structure that only G Newton is weak, and these are some beta 0, beta 2, and beta 3 are some finite numbers.
D larger than 4. A D larger than 4. All your bounds were D larger than 4. There, beta 0 is actually the relevant interaction.
That's right. But even then, as will become more clear, I cannot constrain beta 0, even in D greater than 4. I can only constrain beta 2 and beta 3.
And also, why you don't have like grad phi to the 4 term here, like the usual interaction?
No, that's supposed to be this one. This is just schematic. Yeah, okay. I should have said it. Beta 2 is the partial phi to the 4.
Yeah, sorry. Okay.
This is the one that in your paper was proved to be positive.
Okay.
But that's in the absence of gravity. With gravity, you see that it's shifted a little bit to the left.
Mm-hmm.
It can be a little bit negative. Okay, so what are the assumptions? We have this kind of structure. First assumption is causality, and that implies that the S-matrix should be analytic away from the singularities for complex value of S. So I'm imagining to take U fixed and negative, and S can be anything complex, and it's analytic away from the cut. So that's assumption number 1. Second one is that we have weak coupling. So we already discussed this extensively, and it means that there is no cut at the origin, starting at the origin. It's just some meromorphic function, which looks like 8 pi G Newton. There's a contribution from gravity, which is the exchange of the graviton in the 3 channels. Then there's beta 0 is just a constant. Beta 2 multiplies S squared plus T squared plus U squared, and beta 3 multiplies STU. And there is an infinite sequence of higher derivative corrections. Third assumption is unitarity, which tells us something about how the function looks like on these cuts. Specifically, if one takes an imaginary part, you can expand this into Gegenbauer polynomials with positive coefficients. So it's just these coefficients are like the coupling squares of to the on-shell states. They need to be positive. And finally, crossing symmetry, which just says that if I send S to minus S minus U, which is the same thing as switching T and S, the function is symmetric. So there's some symmetry switching the left and right cut in this plane. So the idea is that these 4 assumptions constrain the S-matrix in various places, and altogether they are very powerful. And their overall consistency places bounds on the beta 2 and beta 3. there's also another assumption which I didn't, well, another property which I didn't list, which is some behavior at large S. And it's a little technical. There's like the Froissart bound. Maybe we can discuss it after the talk in the interest of time. Okay, so how do we use this structure to prove bounds on the couplings? The idea is to use dispersion relations in a novel way. So let me explain to you what these dispersion relations are. Dispersion relations in practice, they are like a quantitative expression of the idea that causality requires the IR and the UV to talk to each other. And it just comes from the fact that holomorphic function integrates to 0 around a closed curve, where the curve doesn't include any singularity. So we just apply this idea to, I mean, this is standard stuff. Okay, I'm not saying this is new. The new part is coming later. So the standard stuff is just to do this integral. You get 0 because there are no singularities in the upper half plane, and then you pull this contour integral onto the singularities. And there are two contributions after you pull the contour. There's a contribution coming from the poles which are equal to 0, and contributions coming from the UV, which come from, they basically look like the discontinuity of the function along the cut. So this, but because the original thing was 0, the second thing must be 0 too. And we are using some boundedness at infinity, like the Froissart bound, to say that we don't need we don't need the arc at infinity. So from this being 0, we get some sort of equality between IR and the UV, that the IR contribution must cancel the UV contribution. And finally, we know that the UV contribution is positive, which imposes some inequalities on the IR contribution. Okay, so that's the rough idea, which has been used in literature many times. Okay, so how do we use it exactly? Okay, one can basically write down.
But I thought again, you had massless particles, and then Froissart bound is I don't think it's applicable for.
That's true. That's strictly speaking, that's true. So I mean, this is like an extra assumption that we can. I think it's true. It's certainly true in string theory. This assumption that we can throw away this cut infinity with enough subtractions.
What would go wrong if you added a mass for the scalar?
I don't think anything would go wrong. It would just make it a little more complicated. It's a good question. We haven't done it. Probably.
But then conclusions on the positivity of the coefficients of some operators change, because you can have that's more technical stuff, but you can have some stuff that's proportional to that mass. Changing your conclusions, but
yeah. All right. So this is what the sum rules that you get look like in practice. So this is like the simplest one. The left-hand side is the IR contribution. It depends on the additional Mandelstam. Okay. So there are two Mandelstams. One of them is being set essentially to 0 because that's where the IR lives, and the other one is a free parameter. So there is a graviton pole t equals 0, and that there is an infinite sequence of higher derivative corrections. So it's the IR, and the right hand side is the UV, which is some average over the heavy states. This is some precise sort of distribution with some positive coefficients of a function depending on t, where p is the Gegenbar polynomial. It just follows from unitarity. Okay, now let's imagine taking this equation, which relates IR and the UV, and making t very small. So t needs to be negative for example, for this Froissart bound to work. For the negative t is the physical region. So t is always real and negative in here. As we send t to 0 from the negative real axis, the left-hand side becomes dominated, and positive. The -1/t is positive and dominates the sum. And as we take t to 0 here, everything sort of collapses to some positive average. But strictly speaking, at t equals 0, it diverges. But you can see that it implies that the positivity of the heavy contributions implies that G Newton must be positive. Okay, so that's nice confirmation of the obvious fact that gravity is attractive. But this pole causes problems. Okay, so for now, let's suppose that there is no gravity. So let's suppose that this first term is not there, this -1/t. Then you can expand around the forward limit, t equals 0, and find expressions for these couplings. So for example, leading order, beta2, when you set t equals 0 in the absence of gravity, you just get that beta2 is positive, because on the right-hand side, you just get 1/m². That's a UV average. And similarly for beta3, you get an expression for beta3, which looks like 3 minus something which is positive as well. And you can use this to show that there is an upper bound on beta3 involving the beta2 and the UV cutoff, because the UV cutoff at m² appears because there's a higher power of small m. So small m is the mass of the exchange particles. Okay, and this is sort of a beautiful story over the last decade or so, which started with this seminal paper, Sergey and friends, and continued up to this year. Okay, but all of this assumes that there is no gravity. So there is a problem, which is that one would like to prove these kinds of bounds by isolating the individual couplings. So one would like to isolate the individual couplings in the presence of gravity, so when there is a pole, but we cannot expand around the forward limit. We just cannot do the Taylor series because it blows up. Okay. So somehow the main point of our paper is that we solve this problem. And let me explain to what the basic idea is. So here is the sum rule, which includes gravity. And the part one of the solution is first to eliminate these higher couplings. So one problem is that there's an infinite sum of couplings on the left-hand side, and you want to just focus on beta2 and beta3. You don't want to be contaminated by the higher couplings, but that's not too hard to do. You can just use crossing symmetry to eliminate them. And I can tell you more details after the talk. So that's not really the too important. It's just a small step. If you do that, you find that that you just get the same sum rule with no corrections. Just the gravity beta2 and beta3 is equal to some average, which is modification of this average. There are some corrections that are also involve these Gegenbaur polynomials. And the second, the key idea is that to prove bounds on these couplings is to forget about the forward limit. So we should not use wave packets localized around the forward limit, because there the gravity dominates, it just blows up. And instead, we should localize around small impact parameter. Okay, so that's the impact parameter, in particular the impact parameter, which is, I should say the impact parameter is like the Fourier dual of t, of the transfer, of the momentum transfer. So to prove these bounds, one needs to localize to impact parameter of the size of the UV cutoff, very small. And this requires going very far from the forward limit. The forward limit is t to 0, and for this to work, one needs to take t of the order of the UV cutoff. Okay. So
these corrections which you have here, they're still sign definite, or?
No, well, they have some sign. They are sign definite enough that you can run the argument. Like there are some complicated, like this. Already, this thing is not sign definite. For if you set t away from 0, this oscillates as a function of m. Only in the forward limit, it's sign definite. And these corrections, I think they. I don't really know.
Sorry, but what is m? You said it wasn't the mass equal to 0 for your particle.
Oh, m. Okay, this is small m.
Mm-hmm. Yes.
Small m. This is average over the heavy state. So this is like a sum over the heavy states, and m is the mass of the heavy state. So we are taking an average of this expression over the heavy states, which are parameterized by their mass m and j, their spin. Okay, these are the exchanged on shell states. Is that okay, Massimo?
Yes.
Okay, so this basically the solution of the problem is a combination of these two papers. The first paper use the forward limit to prove basically that beta 2 is positive without gravity. And the second paper doesn't use the forward limit, but it uses this fixed impact parameter scattering. And what we show is that when you combine the two, you get a precise bound, which is not parametric, which is with an order 1 coefficient. Okay, so here are the results. I already showed you this plot. It uses the idea from the previous slide. There is still a lower bound on beta 2, which is now shifted a little bit to the left, and there is both a lower bound and upper bound on beta 3. And this is what the spectrum looks like at this corner. So it's kind of the reverse of string theory. In string theory, we would get the upper triangle, and here we get the lower triangle. But I'm sort of running short on time, so maybe we can discuss this later. And one can also use the same logic to prove bounds on these higher derivative couplings for various values for various vertical slices, and they now become nicely compact. So the only non-compactness in these bounds is the non-compactness towards positive beta 2. There's also a story in maximal supergravity where you can show that this beta 0, with supergravity, there is like a shift of what is relevant and what is irrelevant because of supersymmetry, and beta 2 must be positive, but also you can prove numerically that it needs to be smaller than 3 using our ideas. And that's consistent with string theory. So in type 2 string theory, beta 2 is 2 times zeta 3, which is 2.4, and that's indeed less than 3. Okay. Oh, sorry. Okay. Okay, maybe let me conclude with the next couple of slides, and then we can do questions after. So what's the summary? We derived some rigorous bounds on EFT couplings in consistent weakly coupled theories of gravity. And the bounds follow from unitarity and causality implemented by dispersion relations. The key new idea was to, instead of thinking about the forward limit, the key idea was to localize the dispersion relation in the transverse impact parameter space. And this completely resolves the notorious difficulties presented by the T-channel graviton pole. And just a small note about the weak coupling. So I guess we already discussed this quite a bit, but really we are only using the weak coupling of the effective field theory, so that we are neglecting the logarithmic cuts which stretch down to s equal to 0. But we are not really assuming weakly coupled deep UV, because the UV only enters through unitarity of the through positivity of the UV couplings. And that is a fact which is true regardless whether the coupling is weak or strong. So basically this means that I think one can correct the analysis away from the weak coupling by incorporating EFT loops. So you can like add the cuts. The cuts are themselves determined by the EFT, and one can try to systematically correct it. But there are some difficulties with that too. Just the rough idea should work. Okay, so now looking ahead a little, this technique generalizes to arbitrary S-matrix elements. I was discussing scalar 2-to-2 scattering, but one can consider graviton scattering, which would be relevant for the CEMZ bounds and so on. So one can envision to elevate this to a systematic Bootstrap program for classifying weakly coupled gravity theories from first principles, and maybe one day prove that that string theory gives the only possibilities, or find something new. Second, you can also consider non-gravitational S-matrices with infinite towers of massive higher spin particles, and use these dispersion relations to explore the space of large engaged theories. So I think that's pretty exciting. Okay, then I have a couple of slides about ADS-CFT and how this connects to my older work on the analytic functionals. and dispersion relations, but I think for now I'm going to skip that, and we can discuss it now if you want. Finally, there are some more vague, and fascinating questions, whether, like, what is the relationship of these techniques to flat space holography, and whether anything like that could work in cosmology, like to have some dispersive sum rules in the Sator space, for example. But currently, I don't know where this will work. But thanks for your attention.
Thank you.
Thank you.
Thank you very much. And now it's time for questions.
May I ask, what's the reason all your bounds were starting at d equal 5? I thought d equal 4 is hard in the presence of gravity because 1 over t pole becomes especially nasty there. But you're saying that you solved that problem. So why you can't do it?
Oh no. Well, it's a different. I guess we solved the problem away from d equal 4. It's essentially in d equal to 4. There's a stronger IR divergence. It's stronger than in strictly greater than d equal to 4. So one would have to impose some IR cutoff in d equal to 4. An example where this is possible is in ADS CFT. So in this whole story, okay, maybe I can go to that slide. So this whole story has a very precise analog for ADS scattering, as we will also discuss in the paper. And in that case, the IR cutoff is just the size of ADS. So there's going to be some logarithmic dependence on L ADS divided by L string. And the divergence can be cured. But in flat space, one would first have to look at a different observable, I think, for them, like there's this like some kind of more IR safe observable than the 2 to 2 S-matrix of phi. Yeah, so the answer is we solve the problem in 4 dimensions in ADS, but not in flat space.
Other questions? I mean, I have two. One is that since you are working to first order in the perturbative expansion of the EFT, why do you talk about cuts? Why aren't these cuts in reality just a sum of poles?
That's a very good question. So that's right. So in string theory, this would just be a sequence of poles. It wouldn't be a cut. But I wanted to emphasize that we are not using that assumption. That we are just using positivity of the imaginary part. So you could imagine that you have a theory which is very weakly coupled. It's not exactly tree level. So like eventually when you go very, very far right on the S-axis, you will have something more complicated than just poles. And the analysis will still be true. Like some black holes will appear here with some positive coefficients, but they won't be. Does it make like? Yeah, I just wanted to stress the fact that we are not using meromorphy, and this allows us to probably correct the story systematically away from the weak coupling by incorporating loops.
Thank you. The second question is that it's not clear to me, what did you do in ADS? Did you use ADS CFT and work with this conformal field theory in the boundary, or did you study field theories in ADS?
Oh, we used ADS CFT. So okay, let me say more about this. Okay, so the analogous question in ADS, well, we can consider weakly coupled gravity theories in ADS, and these are dual to some CFTs on the boundary. There is a famous conjecture due to Hemskerk, Panutnash-Polchinski, and Saleh, which I guess from nowadays is quite obvious, but it just says that if you have a theory with large n and large gap on the boundary, then we should have a local description in the bulk. So local means that these higher derivative vertices are suppressed. And Okay, so now one can use the Bootstrap. Oh, I should say, the analog of the S-matrix is the set of CFT correlators on the boundary, and all of these ideas like dispersion relations and positivity of the imaginary part, they have some very precise analog in the CFT. So, for example, for the structure of the S-matrix has these singularities and some IR contribution. So the analog of that statement is that, well, you can think about the OPE of the primary operator. There's the operator phi, which is some light single trace operator, which is dual to the bulk massless scalar, and its OPE will contain some light contributions and some heavy contributions. So the light contributions is like analogous to the contribution from this 0, and the heavy contributions are analogous to these cuts. There are some double trace operators, maybe some light single traces, and they're composites, but it can be mapped. Then the second element of the story is that the positivity of the imaginary part on the cut becomes the positivity of the double commutator. So the imaginary part of the S-matrix is analogous to the double commutator of the 4-point function. Then the third point is how does one implement causality, where causality is really just the crossing equation of the CFT. So usually we think of crossing equation as the equality of two OPEs, and you can think about it as having this 4-point function for phi fields. And as long as x1 and x3 are space-like separated, then the commutator should vanish. This is the statement of causality. And if you expand these two terms in the commutator using OPEs, you get exactly what is called the crossing equation. And finally, the dispersion relations come from integrating this crossing equation along some light trace. It basically, well, I guess one important point is that for flat space, there were still some murky assumptions, like, for example, the Frossard bound. Is it true with gravity or is it not true with gravity? But in ADS-CFT, all of these assumptions are not there. It's like everything is perfectly rigorous. The Frossard bound is, the analog of the Frossard bound is rigorous. It's just some bound on the Regge behavior of the 4-point function. And these dispersive sum rules are totally rigorous sum rules. And also I think the ADS point of view makes it clear that this weak coupling assumption is not crucial. Like really what one is doing is that, like, proving bounds on the IR is like proving bounds on the anomalous dimensions of double trace operators in some sense from the UV positivity. And okay, everything is simple when n is large, when the coupling is weak, but all the same constraints still exist for finite n, for finite G Newton. But okay, we haven't really explored corrections away from the weak coupling yet.
Sorry, what is the equivalent of weak coupling in ADS?
It's the statement that the OP organizes in this way, that there are some double trace operators which have very small anomalous dimensions. So there's these double trace operators, they are analogs of the two particle states. Mm-hmm. And weak coupling means that their anomalous dimensions are suppressed by some small parameter, which in this case is like the Planck length divided by the ADS length. Okay, so that's the equivalent of weak coupling. But again, we don't need to assume anything about the heavy operators besides them being unitary. So it's just the IR which needs to be weakly coupled, and the UV can be strongly coupled for the argument to work.
IR here means low dimensions, low conformal dimensions.
Yeah, IR means smaller, much smaller than the delta gap, which is like the UV cutoff in the units of ADS radius.
Thank you. Other questions? please, from students maybe.
Yeah. So these bootstrap you're doing are constraining the CFT coupled to gravity.
No, it's the CFT dual to gravity. So it's a CFT on the boundary, which it could be some conformal gauge theory like n equals 4 super else. There's no gravity, but it has a local stress tensor operator, which is dual to the bulk graviton. So you're really just constraining ordinary quantum field theories, and thanks to ADS CFT, learning about gravity in the bulk.
So is this like a kind? Okay, so do you have any idea, or have you checked that any of these constraints on this CFT match some swampland constraint on the quantum gravity part?
That's a great question. Well, it'll be fantastic to say prove the weak gravity conjecture using some similar ideas. It hasn't been done. I guess you could say that these bounds on higher derivative operators are types of swampland constraints. So we proved those. Yeah, I guess it would be nice to see how it fits in with the other swampland constraints like the. Yeah, I think the weak gravity conjecture may be a good thing to try, but. Yeah.
Thank you.
Questions? Any other question? If none, I would like to ask about the Frossard bound. Now, at very, very high energies, the scattering of anything will go through a black hole, and then shouldn't the high energy S-matrix have follow the black hole ansatz, which has a dependence in the complex S-plane that is not Frossard? It has this exponential of S, etc.
Mm-hmm.
So why do you expect Frossard to hold?
Yeah. Well, one answer to this question is that in ADS, in the context of ADS, everything just works. The Frossard bound is rigorous at finite coupling in the presence of black holes. And so it's not really called a Frossard bound. It's a bound that was proved by Simon Caron-Ulot about the Regge limit of 4-point functions. Now, but you can still ask, what does this teach us about flat space? So what are, okay, if we know in ADS it works, how come, what does it mean that?
Didn't you need a Frossard bound to prove your flat space result?
Yes, yeah, I did. Let's see, what's the right way? Yeah, why don't the black holes matter? I think there is a good answer to this question, but I can't remember it. Well, at weak coupling, it's saying weak coupled string theory. It's a theorem. You can just check that the Frossard bound is satisfied, but this, of course, doesn't address your question because your question is precisely about the strongly coupled regime.
The high energy, the UV, right? When you close the circle at infinity.
Yes. Maybe the point is just that you can't really push the circle all the way to infinity. You can sort of push the circle until you can no longer do it, but the contribution of the circle is still much smaller than the other contributions in our sum rule. So I can imagine that to work, and that somehow has to happen when we take the weak coupled limit.
But then you are back to getting squildes rather than sharp bounds, right?
Well, if you can show that this contribution of the circle is suppressed by much higher scale than like the UV cutoff, more like the Planck scale, then I think you're still proving sharp bounds. Yeah, but okay, I'm not very happy about my understanding of exactly this issue. I should understand this better. Yeah, all I can say is that it's true for tree-level string theory. It's true in ADS CFT, and I'm not sure why it's true for for finite coupling amplitudes. You can say it's an assumption, but then why is it a justified assumption?
We have other questions?
Yes, this is maybe it's a naive question. I am a student, but when you, I don't know if I understood properly, but the bounds came, for example, with comparing on the right-hand side some average over the UV theory.
Mm-hmm.
But for example, what do we know from the UV theory for real? I mean, that average is over what? I mean, if you know the UV theory, then basically you know the entire physics. What would you go to the left side of the equation if you know the UV theory?
Mm-hmm. Yeah, exactly. Yeah, very good question. The point is precisely that you don't need to know anything about the UV theory. You just need to know that it's unitary, these it's a positive average over UV stuff. It doesn't matter what the UV stuff is. The bound will always be true. It just follows from positivity of the couplings to the UV physics. Okay, maybe I should write what this average is exactly. So this thing just means that you're summing over the operators of the imaginary part.
Sorry, you should stop sharing the screen though, because otherwise you get only get a small icon, right? I think. So.
Oh, okay.
The blackboard is small there.
Oh, is blackboard is okay.
Okay.
Okay. So this is just like sum over the UV operators. Of some. Okay. These are the couplings. The UV physics, and times some function which depends on the masses and the spins. So just we know what this function is. This is just what enters into the sum rules, and we know that this is positive. We don't know the values of the f's, but we know they are positive, and that's all that you need to conclude those bounds.
Thank you. So do we have other questions? Oh. So if not, so over question 1, 2, 3. Okay, so we'll thank Dalimil for the time, for the talk, and so thank you.
Thanks very much.
Thank you.
Have a nice weekend. Thanks.
You too.